15,000 light-years, a number so vast it compels you to pause, draw in a deep breath, and ponder whether our entire existence is merely a fleeting instant in the endless river of time. Picture yourself seated by an open window on a sweltering summer evening, the incessant chorus of cicadas in the garden blending with the faint, sweet scent of milk flower blossoms drifting on the breeze. You lift your gaze to the inky black sky, where stars twinkle like tiny embers from a distant past. Somewhere out there, precisely 15,000 light-years from us, an expanse so immense that light from a star would take 15,000 years to traverse it. Back when our ancestors were just beginning to domesticate livestock, shivering beside campfires under the icy hailstorms of the Ice Age, something is calculating with terrifying precision. Every 44 minutes, it unleashes bursts of radio waves and X-rays directly toward our Earth, like a persistent whisper emerging from the cosmic void, slicing through dense stardust and languid clouds of gas. Each eruption lasts exactly 2 minutes, a duration long enough for you to brew a steaming cup of tea, listening to the kettle's rumbling boil and inhaling the gentle aroma of tea leaves as steam rises, yet short enough to startle you when you realize that in that very moment, something remote is awakening and slumbering to its own inscrutable rhythm. Then comes the silence, a profound hush spanning 42 minutes, where space itself seems to hold its breath, leaving only the invisible murmur of cosmic winds whispering through vast emptiness. And then it happens again, and again, like an ancient clock forged from the heart of a long-dead star, never deviating by a single second. Scientists have dubbed it ASKAP 1832-0911, a stark, utilitarian name carrying celestial coordinates, and the moniker of the telescope that unveiled it. But behind those digits lies a blend of awe and anticipation, a sensation as if the universe is toying with us, murmuring, "Do you think you know it all? Look closer." They cannot tell you precisely what it is, not with certainty. Even after months spent in brightly lit laboratories, amid the ceaseless hum of computers and the thick, pervasive aroma of strong coffee, debating fervently until voices grow hoarse from exhaustion and exhilaration. It does not align with any known pulsar, those neutron stars spinning like cosmic firewheels, flashing several times per second with echoing ticks reverberating across space. Nor is it any magnetar, those colossal magnetic behemoths that shred atoms and unleash stellar quakes, so profound they leave physicists shaking their heads in wonder. Neither does it resemble any binary system we have observed, those deadly duets of white dwarfs orbiting in a fatal waltz, exchanging matter like desperate lovers in the gloom. Some astronomers, their eyes weary from endless nights at the eyepiece, suspect it might be a novel kind of dead star, a remnant from a supernova explosion, where the stellar core collapsed, not into the familiar neutron star, but into something different, something murmuring secrets about stellar endings we have never dreamed of. Others, hearts pounding with insatiable curiosity, propose it unveils physics we have never imagined, laws bent at the edge of relativity, where magnetic fields, so intense they warp spacetime itself, sending electrons spiraling like frenzied dancers in a chaotic symphony. To illuminate these mystic pillars with us, those moments that make you feel both insignificant and profound, like standing at the precipice of an infinite ocean, with waves lapping rhythmically and salty wind brushing your skin. Please like this video and subscribe. We embark on this journey together now, where each discovery is a fresh breeze sweeping through your mind, carrying the scent of stardust and the whispers of distant suns. Late in the year 2024, as the world buzzed with everyday concerns, the clamor of traffic on bustling streets, the comforting smell of toasted bread wafting from a neighbor's kitchen, and sudden drizzles soaking sidewalks, astronomers at the International Center for Radio Astronomy Research, ensconced in quiet offices bathed in the blue glow of computer screens illuminating their faces, spotted something that should not exist. It was a late evening in Perth, Australia, where the red desert glowed faintly under a hazy moon and winds howled through parched scrub, when a signal abruptly materialized on their monitors, flashing like an unexpected spark in the dark void of the screen before vanishing. only to return with unnerving persistence. The pattern repeated without variation, like a steady heartbeat from the universe's core, prompting researchers to rub their eyes, double-check the data, their own hearts racing with a mix of skepticism and thrill. Was this a glitch, or an invitation from antiquity? The Australian Square Kilometre Array Pathfinder Telescope, or ASKAP, a sprawling array of massive dishes scattered across Western Australia's desert, like gigantic ears attuned to the cosmos. With desert winds whistling through metal antennas and the scent of cracked red earth under relentless sun, had been scanning the southern sky when it detected these radio energy pulses, arriving with mechanical precision, each lasting exactly 2 minutes, a span you might envision as the steady ticking of an old wall clock in your grandmother's home, reassuring in its regularity. The intervals between them measured 44.2 minutes each time, a figure so exact it unsettled scientists, evoking images of a meticulously crafted machine other than the universe's natural chaos, where everything drifts on stellar winds and gravitational pulls. Natural objects typically waver. After all, stars wobble in their spins, crafting gentle but imperfect dances, like a child taking its first tottering steps. Orbits decay gradually over time, like faded old romances in memory. Magnetic fields fluctuate like ripples on a serene lake stirred by a breeze. Yet here was something in the deep void, maintaining a rhythm more precise than most human-made clocks on Earth. Your quartz watch beeping steadily on your wrist, or the insistent alarm jolting you from dreams each morning. Researchers scrutinize their instruments, dusting off antenna dishes coated in desert grit under Australia's scorching sun, where sweat beaded on brows and weary laughter echoed among colleagues. They pored over data processing pipelines, endless lines of code running on computers with fans whirring like secretive murmurs. They hunted for timestamp errors, cross-referencing every second against observations from telescopes worldwide. Everything checked out, and their hearts sank with a mix of relief and apprehension. This was real, something truly unfolding out there, 15,000 light-years distant, where the light we see today departed when humanity first tilled soil. Golden wheat fields swaying under ancient Egyptian suns, children's laughter echoing amid thatched huts, and weary but joyful farmers harvesting inaugural crops. The radio waves completed their voyage now, embarking at civilization's dawn, when Nile gods were still worshipped along the glittering riverbanks, and throughout that odyssey, the source had flickered on, off, never missing a beat, like a steadfast old friend, dispatching letters, despite unanswered replies. Radio telescopes detect invisible light, waves our eyes fatigued from long days staring at phone screens, amid the ambient music from a nearby cafe cannot perceive. Yet they convey information across immense distances, piercing thick stardust and drifting gas clouds like pale ghosts in cosmic fog. When charged particles accelerate in strong magnetic fields, they emit radio energy, a process akin to tiny electrons caught in a magnetic vortex, spiraling and colliding to produce unseen hisses, echoing through frigid space, where temperatures plunge to -270 degrees Celsius, and no sound travels unless you imagine the whispers of fundamental particles. Pulsars do this, neutron stars whirling with thumping thuds like colossal propellers. Some binary systems too, where two white dwarf corpses exchange matter in a lethal dance, sparking flares like New Year's fireworks. But those objects pulse rapidly, several times per second, or at most every few seconds. A frantic rhythm, a marathon runner's heartbeat. Nothing in science sustains a 44-minute cycle, a span vast enough to binge-watch an entire episode of a long-running series, absorbing laughter from the screen, and the buttery scent of popcorn filling a cozy living room. The research team at ASKAP J1832-0911 delved to the telescope and its sky coordinates, those arid numbers like a cosmic postal address, and they commenced follow-up observations immediately, hearts quickening with urgency, like explorers spotting strange footprints on a desolate beach. Each time they aimed instruments at that patch of space, a dim sky region with no standout features, Just faint constellations and cosmic winds murmuring. They caught the signal on schedule. You could set your watch by it. An antique timepiece with a second hand ticking steadily on a weathered wooden desk. Then they delved into archival data. Vast repositories from the Murchison Wide Field Array, another Australian telescope, amid crimson deserts. Kangaroos bounding distantly and baked earth scenting the air, which had imaged that sky patch 4 years in surveys. Ghostly images like abstract paintings in invisible light. Researchers revisited old observations, hunching over computers 4 hours with mouse clicks resounding in hush rooms. And there it was, the same signal, same timing, stretching back years. Like correspondence from a long-lost friend you only now recognize. This thing had been broadcasting long before anyone noticed, perhaps since woolly mammoths roamed icy steppes, their heavy footfalls crunching snow and breath fogging in biting air. And while brightness varied, some pulses arriving stronger than others, like larger waves on a calm sea, the interval never wavered. Over 6 months of monitoring, overall intensity faded markedly, evoking a poignant curiosity among scientists. Was it tiring, or merely part of a grander cadence? Yet the clock ticked flawlessly, 44.2 minutes, 2 minutes on, like a cosmic lighthouse, save that lighthouses are built by purposeful intelligences, waves crashing below and golden beams piercing night fog. Scientists began proposing explanations, lively discussions in online conferences, laced with fatigued chuckles and questions pouring like rain. Perhaps a neutron star spinning excruciatingly slowly, akin to a leisurely elder rocking on a porch with lazy but steadfast rhythm. Maybe a white dwarf binary where two corpses orbit, exchanging magnetic whispers across frigid voids, sparking flares like echoes of lost love, or something tied to unseen magnetic interplay, field lines twisting like invisible threads, weaving the cosmic veil. Each theory harbored flaws, leaving unanswered queries like puzzle pieces missing a corner, keeping researchers awake nights, staring at dark ceilings with clocks ticking reminders of passing time. Conventional timing suggests rotation or orbit, but 44 minutes occupies a peculiar niche, too slow for any detected neutron star spin pulses, whirring like jet engines, and too swift for most white dwarf binaries, whose orbits stretch hours like languid moonlit waltzes. The object fills a void in our comprehension, where known physics offers no cozy answers. A chasm evoking standing at an abyss's edge, cold winds rising from below and distant echoes of undiscovered secrets. Then someone checked if any X-ray telescopes had peered at the same spot, and what they found deepened the enigma, as if the universe chuckled, layering more mist on an already hazy canvas. Interstellar space is not truly empty. Yet it might as well be, a vast expanse where silence resounds like wordless music. The journey from pulsing object to Earth spans 15,000 light-years. Imagine each recorded year of human history as a mile you would need to trek that distance 3,000 times. Heavy footsteps pounding scorching sands, sweat dripping and winds howling past ears, to cover but a fraction of this signal's path. Radio waves and X-rays travel toward us at light speed, the universe's swiftest velocity, one that dizzies if contemplated, like plummeting from the world's tallest peak, with winds screaming and heart thundering, yet they require 15,000 years to arrive. The light reaching your eyes tonight began its trek in the last ice age, when woolly mammoths still lumbered across Earth, feet crunching pristine snow and breaths clouding frigid air. Humans huddled in small bands, hunting with crude stone tools, campfires crackling and roasted meat scents filling dim caves. All written history unfolded, empires rising and crumbling amid clashing swords and vanquished cries, wars and peaces forged while these special photons traverse the void, solitary light particles wandering darkness, bearing memories of a bygone world. The signal attenuates little over this gulf. Radio waves spread as they propagate, like ripples on a tranquil pond, disturbed by a pebble. But they persist. The object must shine extraordinarily to remain detectable after crossing such breadth, a luminosity prompting cheers in control rooms, applause echoing and smiles beaming on weary faces. Astronomers gauged its brightness in Yanskis, a unit honoring Karl Jansky, Radio astronomers pioneer a quiet man with thick glasses and long nights at rotating antennas. Tuning into hisses from the Milky Way's core, an alien tune. This source peaks at 10 to 20 Yanskis during active phases, rendering it among the brightest long-period transients ever found. Latest reports from Chandra in May 2025, when NASA scientists published in Nature, describe it as a quirky beacon defying familiar models. Between us and the source lies mostly hydrogen, lone atoms drifting interstellar medium, perhaps 1 per cubic centimeter sparse indeed, like dust motes suspended in a vast room with gentle winds stirring curtains. Multiply across 15,000 light-years, though, and you accumulate substantial material, tenuous but tenacious gas clouds, absorbing visible light, yet permitting radio waves to glide like phantoms. Radio waves traverse this gas with minimal interference, explaining why radio astronomy peers deep into galaxies, while visible light halts at dust shrouds, those grey silk veils obscuring views, rendering our night sky but a sliver of reality. The signal also pierces Earth's atmosphere before reaching telescopes. Our planet's ionosphere, a high-altitude layer of charged particles potentially distorting radio waves, like stones rippling pond surfaces. ASKAP's Western Australia site lies in a radio-quiet zone, shielded from human interference. No buzzing cell towers, no blaring broadcasts, just red deserts and scientific instruments, listening to the cosmos, amid howling winds and parched earth scents under blazing sun. The source resides in our galaxy, the Milky Way, cosmically neighborly, like someone blocks away with distant nighttime dog barks. Yet our galaxy spans 100,000 light-years. A starry river meandering darkness, with billions of suns murmuring. This object sits roughly 15% along the path from us toward the galactic core, thousands of stars intervening, gas and dust clouds veiling visible sight like thick fog walls. Only radio and X-ray observations penetrate that century line, waves slipping like specters, bearing tidings from yesteryear. 15,000 light-years means we view the object as it was, not as it is, a delayed snapshot from light speed limits, where it might still pulse identically. It's tick-tock echoing space. It could have ceased broadcasting 10,000 years ago, and we would not know for 5,000 more. A protracted wait evoking solitude amid timelines. Or it might have transformed utterly, evolving anew or perishing, like a lone star fading into gloom, leaving cosmic winds whispering voids. We watch ancient history unfold in real time, lagged by universal speed caps, a slow-motion film with millennia-spanning shots, each frame a bygone memory. The signal traverses star-birth zones, molecular clouds enshrouded, stellar nurseries where gravity draws gas into new suns, thuds of compressing gas, and first light dawning like Earth's inaugural sunrise. It voyages territories patrolled by rogue black holes, invisible monsters bending space, like giant hands twisting reality. Yet radio waves arrive intact, message repeating every 44 minutes. 4 years, perhaps centuries or millennia. It broadcast unnoticed, until an eureka moment in a control room with cheers resounding and hugs exchanged across oceans. But detection raises more questions than answers, like opening an old house's door to uncover hidden chambers beyond, each dusty and whispering secrets. The bursts do not fade gracefully. At appointed instants, the source ignites like a switch flipped in darkness, radio emission surging from zero to peak intensity in seconds. Abrupt shift startling like thunder in a quiet midnight. The signal holds strong for precisely 120 seconds, then severs sharply, silence reclaiming 42 minutes before the cycle renews. A loop evoking a melancholic song with soaring notes abruptly silenced. This sharp on-off informs scientists of something crucial. Whatever generates these pulses must be extraordinarily efficient and tightly controlled, like a tightrope walker traversing a gale without falter. Random processes yield gradual shifts, like drizzling rain pattering roofs. Chaotic systems produce erratic patterns, like storms with random lightning flashes. This object operates with machine-like precision. During 2-minute activity, Much unfolds concurrently. Radio waves flood a broad frequency band, emission highly polarized, meaning waves oscillate in organized patterns rather than random directions. This polarization indicates strong magnetic fields at source, field lines coiling like massive ropes constricting plasma, and it hints we behold beamed radiation, like a searchlight momentarily aimed our way from something rotating or orbiting, a beam sweeping darkness, like a torch in deep woods. The 2-minute span allows detailed data capture, yet preserves mystery. Hours-long pulses might suggest orbiting behind a companion star, like a ship vanishing in fog. Millisecond bursts would fit known pulsars. Sparrow heart flutters. 2 minutes claims an awkward middle ground. Scientists dissect each into subcomponents. Radio emission arrives not smoothly but structured, with subpulses, intensity varying second to second within the window greater than expected. These oscillations signaling complex source processes, perhaps matter funneling into magnetic fields, scorching gas streams like lava rivers, electrons helically threading twisted fields, birthing invisible light vortices, or something utterly alien, leaving physicists scratching heads in late meetings, pencils tapping wooden tables amid vending machine cookie scents. The source emits across multiple radio frequencies simultaneously. Low frequency and high frequency observations alike detect pulses. This broadband emission demanding energetic processes slow. Cool objects yield narrow light spectra, like a candle flickering in wind. Hot, violent events spawn broad spectra, like explosive New Year's fireworks. Whatever powers this, temperature seems an odd concept for radio transients, but astronomers use brightness temperature to describe apparent energy levels. This object displays billions of Kelvin boring activity compared to our sun's surface at 6,000 Kelvin, numbers implying harsh conditions, perhaps particles accelerated near light speed. A velocity evoking spaceflight, with winds roaring past and meteors streaking by. Each 2-minute burst arrives nearly identical in cycle phase, graphing signal over time. Pulses align near perfectly. This phase stability means whatever clocks the object is exceedingly stable. Tidal forces, field decays, gravitational tugs, all drift-inducing factors seem negligible, like a serene river flowing desert unbound by sands. The window matters too, dictating telescope feasibility. 2 minutes suffices for multi-instrument coordination, spectra acquisition, polarization measurement, real-time variation tracking amid receiver hums and data streaming screens. But its brevity demands precise timing. Miss the window, await another 44 minutes. A tense vigil like awaiting word from distant kin. Clock ticks resounding in mind. This scheduling poses challenges. Telescope time is precious and contested. Convincing committees to allocate resources for observing empty sky, 42 of 44 minutes, requires robust justification. Lengthy presentations, with formula-laden slides and fervent young researcher voices. Fortunately, regularity aids. Point telescopes, await ticks, source delivers predictably. But radio emission tells half the tale. Peering at the spot with different eyes revealed the unanticipated. Radio waves being light eyes cannot detect. Envision the electromagnetic spectrum, a piano keyboard stretching beyond visible octaves, visible light a middle slice, radio filling bass notes, lower energy, longer wavelengths. Your FM radio catches 3-meter waves, cell phones 10-centimeter ones, ASKAP detects 4 to 12-centimeter waves, ideally suited to slice cosmic dust like knives through fog. These waves behave like visible light. In many ways, they travel same speed, focus via dishes and mirrors, reflect off objects and cast shadows, but long wavelengths grant unique traits. They slip through gas clouds, blocking visible light entirely, emerging unscathed from newborn star hideouts behind thick dust curtains. Radio astronomy began serendipitously in 1933 when Carl Jansky, at Bell Telephone Laboratories, tracked static sources interfering radio communications. He built a rotating antenna, detecting hisses from Milky Way's center. No one paid much heed then. That is like an ignored whisper amid urban din. First radio telescopes built post-World War II using surplus radar gear. Bomb echoes haunting memories, and hot metal scents from factories. Modern radio telescopes differ from optical ones. You imagine they are vast dishes, sometimes hundreds meters wide, gathering and focusing radio waves onto receivers. ASKAP comprises 36 12-meter dishes, spread 6 kilometers across Australian deserts, operating as interferometer, combining signals for sharper images as radio waves strike dishes, reflected to central receivers, where sensitive electronics amplify and digitize data, akin to your home satellite dish catching TV signals, but vastly more intricate. Receiver crackles and data flowing screenward like rivers. Modern receivers detect waves, so faint total energy from all built radio telescopes equals less than a snowflake falling. Astonishing sensitivity enabling detection of this pulsar's emission. Bright by astronomical standards, yet undetectable sans specialized gear. Arriving waves carry origin tails. Frequencies reveal electron energies producing them. Polarization maps field structures. Timing variations indicate motion or spin. Radio observations offer another edge. Operable day and night. Rain or shine clouds block not radio waves. Sunlight drowns not them. Telescopes track skies ceaselessly. Desert winds howling overhead, stars twinkling. Thus researchers amass years of 44-minute cycle data. Source pulsing, whether watched or not. The source emits mainly in narrow frequency band. Unusual, most radio sources yield broad emission across frequencies, or narrow at atomic transition specifics. This midway act suggests emission mechanism astronomers incompletely grasp. Are ADIO waves measurable for polarization? Light oscillating with polarization describing direction. This signal shows linear polarization. Waves vibrating mainly one way. High degree, often 50% or more only magnetic fields produce such organized emission. Fields must be potent and orderly. All this from invisible light. Waves longer than your outstretched hand spanning voids, but radio surprise first. Peering same point with even stronger light detectors. Mystery compounded, like opening ancient book to inkless pages, revealing under special light. NASA's Chandra X-ray Observatory serendipitously scans same sky swath purely by chance. Chandra orbits Earth elliptically, reaching over 130,000 kilometers at apogee, advantageously above atmosphere, blocking X-rays, detecting high-energy photons from cosmic sources amid orbital hush and blue Earth gleaming below. That specific day, Chandra observes supernova remnant, expanding debris cloud from exploded star. Blast echo from thousands years past. Remnant coincidentally same sky region as radio source. X-rays energetic, carrying 1,000 times visible photon energy and millions times radio. Producing X-rays demands violent scorching gas, strong fields, or particles accelerated extreme speeds. Space X-rays often from matter accreting black holes, neutron star surfaces, or gas heated millions degrees in supernova shocks. Plasma booms colliding and blinding light. Initial researchers disconnected Chandra data from radio observations, separate projects, but radio team announcing mysterious pulsar coordinates. Someone noted overlap with Chandra field. Retrieving data. Timing analysis revealed pulses X-ray bursts every 44.2 minutes, lasting to minutes. Perfectly synced with radio emission. This changed everything. Previously, astronomers might posit radio from low-energy processes, perhaps electrons spiraling weakish fields, but X-ray capture demands dramatic explanations, something they're accelerating particles to astonishing energies, or heating matter to atom-tearing temperatures. X-ray emission faint versus radio brightness, but undeniably present. Chandra detected photons 0.3 to 8 kiloelectronvolts, soft X-rays, spectrum's lower energy end, yet vastly more energetic than eyes perceive. Flux varies pulse to pulse like radio, but cycle and changing, simultaneous radio and X-ray emission imposes key theoretical constraints. Any explanation must account same object, producing both radiations in perfect sync. If from different sites or mechanisms, expect time lags or phase offsets. Instead, they coincide, suggesting common origin. Phase alignment precise plotting 44-minute cycle. Radio and X-ray peaks align within measurement error. This means whatever process bursts radio also bursts X-rays, or both stem same fundamental event, perhaps particles accelerated along field lines, emitting both radiations concurrently. Maybe same shockwave spawning both. Chandra's narrow view made discovery improbable. Telescope observes sky slivers at once, while ASKAP sweeps broad areas. Odds Chandra randomly observing exact spot precise. ASKAP detection moment minuscule. Source pinpoint. Astronomers call this serendipity, but likeliest accident in recent astronomy. May 2025 Nature report. NRL and international researchers describe golden coincidence, ushering multi-wavelength astronomy new chapter. X-ray data reveals more. Over months, both radio and X-ray emissions faded substantially. Source dimming though timing unaltered. This coordinated dimming both wavelengths strengthens emission mechanism link. Few other long-period transient detected in X-rays, making this first exceptionally anomalous, or suggesting similar objects emit X-rays undetected mid-act. Chandra observations simply fortuitous timing, but luck begets questions. How many more lurk in our galaxy, pulsing unseen like desert buried gems awaiting unearthing? Before 2022, astronomers unaware such objects existed. That year, International Center for Radio Astronomy researchers announced 18-minute radio pulsar discovery, naming Gleam XJ1832-0911. Its surface survey data, visible months, then vanished unlike anything before. Pulsars pulse per second or fraction. This 18 minutes between beats. Announcement sparked archival hunts if one exists. Others hide and examine slow cycles. Global teams reprocessed old survey data, seeking signals appearing disappearing minute to hour timescales. More found. ASKAP J1832-0911 with 54-minute pulses. GPJ 1839-10 with 22-minute intervals active undetected 3 decades. Chime J0630+25 with 7-minute cycle. Each expanded known enigmatic object population. Scientists coined long-period transients, term transient meaning on-off, not steady glow. Long distinguishing from millisecond pulsars and fast variables. Descriptive name reveals not essence. Current catalog lists about 10 confirmed examples, small population, but astronomers suspect severe undersampling. Objects hard detect, most radio surveys snapshot skies. Source off during snapshot. Invisible. Repeated same area observations or continuous monitoring needed catch them. Objects diverse, some steady years. Others appear weeks or months, then vanish perhaps forever. Some highly polarized radio, others less, some bright. Others detection limit faint. Diversity suggests long period transients, not single type, but multiple sharing slow periodicity. None fit cozy existing categories, not classic pulsars, fast spinning neutron stars, not typical binaries orbiting stars, not magnetars, though some possibly evolved old magnetars. White dwarf binaries possibility for some. Existence challenges compact object basics, neutron stars slow aging, but no theory predicts continued radio emission at glacier slow spins. Fields decay. Outflows cease, yet these defy expectations. Some astronomers propose long-period transients represent formation pathways, converging similar observables, perhaps some supermagnetized neutron stars, others white dwarf binaries. Few wholly unimagined things, all spawning slow steady radio pulses via varied mechanisms. Rarity complicates, study 10 examples, each behaving slightly differently. Hard draw general conclusions. Astronomers need more discoveries. Multi-wavelength observations, known examples. Patterns revealing fundamental physics. Thus X-ray emission. Find anomalous first multi-wavelength glimpse, any long-period transient. First peak high energy processes these systems. New window, whatever strange physics births these tickers, but deepens core mystery. as this specific source refuses simple fit. Latest June 2025 SCI News and NASA updates. Researchers debate aged magnetar or ultra-strong magnetic white dwarf. Chandra data showing continued fading, forcing model tweaks. Pulsars are dead stars spinning like cosmic torches, we know them well. Massive star exploding supernova. Core collapsing neutron star. These objects sun-massive, but 20-kilometer spheres. Spinning fast, sometimes hundreds times second, because core collapse conserves angular momentum. Slow spinning star becoming fast neutron star, like figure skater accelerating arms tucked. Neutron stars possess strong fields, trillions times Earth's, spinning. Fields accelerate charged particles near magnetic poles, particles emitting radio beams. If Earth happens beam path, detect pulse, each rotation beam sweeps us. Model explains thousands pulsars, periods millisecond to seconds, slowing over time as rotational energy dissipates. They follow predictable patterns. Physics well understood, fitting observations elegantly. 44-minute source cannot be this pulsar type period, thousands times longer. Neutron star spinning 44 minutes, wants to slow, generate magnetic structure birthing radio beams. Dynamo sustaining pulsar fields, requires faster spin below certain speed. Emission simply ceases. This shutdown called pulsar deathline. Aging pulsars slowing, crossing boundary, becoming undetectable. Fastest pre-death spin varies field strength, but always far short of 44 minutes. No standard pulsar theory permits emission slow. Perhaps object not spinning, but orbiting binary pulsars exist. Neutron star orbiting companion, yielding steady patterns, orbital motion, but 44 minutes too short. Most neutron star pair orbits and emission traits mismatch binary pulsar systems. Some neutron stars accrete companion matter in falling material, releasing energy, birthing X-rays and radio, called low-mass X-ray binaries or spider pulsars, configuration dependent. 44-minute source shows similarities, but phase relation radio X-ray wrong in accretion systems. Expect X-rays from hotspots, matter hitting neutron surface, while radio from jets or corona. Timings differ here since radio brightness poses issue. Active phases source pumps enormous radio power. If rotational energy, neutron star needs vast rotational kinetic, but 44-minute spinner possesses comparatively little. Numbers do not add. Source exhaust energy reservoir far quicker. Observations allow. Pulsar emission usually frequency stable. Pulses metronome precise. This maintains precise period, but varies brightness pulse to pulse, and fades months in usual standard pulsars. High radio polarization matches pulsars, indicating magnetic involvement. Broadband radio emission pulsar-like, but similarities heighten differences baffling, as if object yearns pulsar, but defies rules. Astronomers fitted data, every known pulsar model, young, old, millisecond, magnetar. Exotic variants, nothing works. Each predicts unobserved traits or fails explain observed. Leaves to possibilities. Object not neutron star. Or neutron star doing unprecedented thing. SCI fee novel, but real. Pages, formulas, and Chandra, May 2025 data. Some neutron stars possess fields atom shredding strong. These ultramagnetized, dubbed magnetars. Field strengths 10 to 14 or 15 Gauss, Hertz half Gauss. Sun's peaks thousands. Fields incomprehensibly potent. Warping space vacuum. Birthing exotic matter states. Electrons Landau quantized elongated orbits. Spawn stellar quakes crust. Earthquakes releasing seconds energy exceeding sun's yearly output. Accelerate particles birthing gamma ray burst. Visible half universe. About 30 Milky Way magnetars known. Mostly young, thousands years old. Spinning 2 to 12 seconds faster. 44-minute source, but slower. Typical pulsars. Emit steady X-rays, hot surfaces, and occasional spectacular bursts. Field reconfigurations. 44-minute source could be magnetar, old one, perhaps slowed extraordinarily, developing unknown phase. Theory appealing magnetars birth both radio and X-rays. Potent fields accelerating particles. Observable radiation. High polarization fits field production. Some magnetars show periodic emission, though much shorter periods, but problems immediate. Magnetar field's decay time. After hundreds years, weakening below high energy emission threshold, old magnetar should effectively dead, not broadcasting strong radio and X-ray pulses. 44-minute period suggests harsh age conflicting observed activity. Even if field somehow persists strong, spin period trouble magnetar emission models rely star rotation birthing pulses. Spinning, field sweep space generating electric fields, accelerating particles radiating, but 44-minute period renders mechanism inefficient, spin slow, electric field generated significantly weaker. Some astronomers suggest magnetar not solitary, perhaps companion star, 44 minutes reflecting orbital cycle not spin. In falling companion material fueling magnetar, magnetic interactions birthing periodic emission. Binary magnetar scenario resolves energy issue, accretion provides rotation independent power source. Explains continued activity despite age. Accounts both radio and X-ray via system mechanisms. However, observations contradict simple binary model in typical accretion. X-rays and radio from different regions phase showing offsets. X-rays originate near neutron surface, in falling matter, heating millions degrees. Radio from outer jets or corona not perfect sync. X-ray emission spectrum of fully matching accreting magnetar expectations, temperature off. Flux to variable, something emission mechanism differs known systems. Perhaps magnetar hypothesis partially right, 500,000 year or older magnetar field decayed substantially, but stronger typical old neutron stars, perhaps undergoing late life reactivation drawing interior reserves. Perhaps wobbling spin birthing complex emission patterns unseen before. All possible data neither conclusively supports nor excludes magnetar explanation. Remains contender among several. Each flaws. Not all dead stars, neutron stars, most stars including sun-end white dwarfs. Fuel exhausted star sheds outer layers, leaving hot dense core Earth-sized, but have sun mass. White dwarf cools billions years, eventually dimming darkness like guttering candle night wind. White dwarfs can possess fields, some thousands or millions Gauss impressive, but far weaker magnetars. However, these magnetic white dwarfs exhibit intriguing behaviors. Birthing periodic emission paired companions binaries. 44-minute source could be white dwarf binary to corpses orbiting every 44 minutes. Locked tight embrace. One magnetic white dwarf, other low mass red dwarf or another white dwarf. Matter flowing guided fields birthing observable X-ray and radio emission. Model precedent to other long period transients, linked white dwarf binary spectra. J1832-0911 type pair white dwarfs plus red dwarf orbiting every 2.9 hours. ILTJ 1101 plus 5521 shows similar binary signs. Thus white dwarf binaries certainly birth long transient behavior. White dwarf binary systems sustained stable orbits matching 44-minute cycle. Orbital mechanics work perfectly, stars circling, system parts coming view. Emission could beamed, seeing pulses specific Earth-aligned directions. 2-minute pulse duration, representing time configuration favorable. Binary magnetic interactions impressive, white dwarf field lines sweeping companion or interflowing matter accelerating particles. Particles radiating radio, if field strong and geometry right. X-rays birthed concurrently via synchrotron or heating material, high temperatures, field collisions. Scenario resolves neutron star energy trouble, binary interactions provide continuous power source. Gravitational potential from infalling matter or tidal interactions powering emission millions years. System not reliant stored rotational or magnetic energy. Radio X-ray phase relation easier explain in binary. Both emissions stemming same interaction region, naturally explaining sync. Field sweeping companion triggering both radiations simultaneously. But significant issues remain required. Field strength extreme white dwarf. Birthing observed radio and X-ray brightness with traits. White dwarf needs least 100 million Gauss, perhaps hundreds millions. While known magnetic white dwarfs 10 to 100 million Gauss fields exist, exceedingly rare no confirmed white dwarf field strong enough comfortably explain all observations. Proposed strength exceeds prior detections. Upper theoretical white dwarf magnetic field predictions, perhaps beyond current models, allow months-long variability challenges to why stable binary dim substantially half-year. Orbital evolution millions years not months, perhaps varying material flow, perhaps self-altering field, maybe orbital plane precessing, none fully satisfying. Optical observations yet identify companion if red dwarf, orbiting white dwarf, visible, region crowded stars complicating identification, but future observations resolve. If no companion exists, white dwarf binary theory fails, thus explanation like magnetar hypothesis, viable, but problematic. Something right, something wrong. 44.2 minutes defies everything period occupies gap known cosmic clocks. Pulsars millisecond to seconds, binary orbits hours to days nothing bridges. 44 minutes theoretical void, no standard astronomical process operates. Consider rotation 44-minute neutron star spins to slow birth pulsar emission, centrifugal forces negligible, dynamo sustaining field should not function slow spin. Slowest detected pulsar seconds not minutes. White dwarf spin any speed, but rarely periodic radio signals. Few minutes still hour spin cycles in binaries, where orbital cycle drives emission not spin. Solitary 44-minute white dwarf invisible. Consider orbit to objects. Orbiting 44 minutes must close. Short period white dwarf binaries exist, but death spirals. Losing energy gravitational waves slowly merging. Perhaps 44-minute source. Such system trapped final pre-merger phase, but gravitational wave emission predicts measurable orbital period change months or years observations. Orbit shrink. Period decrease no such change detected. 44 minutes and changing measurement precision. If gravitational waves draining orbital energy, doing imperceptibly slow detect, suggesting system not near merger short period implies. Perhaps period reflects wholly different maybe beat frequency to interacting cycles, harmonic some process. Time field lines reconnecting post-tidal stretch. Possibilities speculative no detailed models test. Period regularity adds mystery layer years observations. Cycle unchanged fraction second. Stability indicates stable clock mechanism. Immune random or external perturbations. Rotation and orbit provide such stability few other astronomical processes do. Stability excludes strange scenarios source, not randomly flickering, not responding accretion rate changes, not tombs surrounding gas cloud interactions. Something core maintains iron discipline 44-minute rhythm. 2-minute pulse duration noteworthy 2y specifically 2. Active to quiet ratio about 1:22. Ratio not obvious geometric factor. If seeing sweeper, like lighthouse beam, expect ratio beam with viewing angle related, but numbers not simple geometry correspond. Perhaps pulse duration reflects material flow time along field lines system part to part. Perhaps energy accumulation release time. Perhaps light travel time across key system region. All plausible none confirmed. Astronomers checked period frequency dependent some pulsars show dispersion. Different radio frequencies, arriving slightly delayed. Interstellar plasma interaction. Source shows normal dispersion matching distance, but pulse itself same phase, all observed frequencies. Whatever births emission coherent across spectrum. Most frustrating 44 minutes feels intentional. Short enough requiring compact objects. Long enough challenging standard models. Long enough continuous observation challenge. But short enough patient observers capture multiple cycles night. If universe design source puzzle astronomers, shows cycle well, radio and X-ray arrive together, not randomly, but necessarily in multi-wavelength astronomy. Different lights often different object regions. Observing active galaxy, optical from stars, infrared warm dust, radio jets, X-rays hot gas, near central black hole. Each wavelength different story part. Emissions different regions, usually phase offsets X-ray pulses one rate, radio another, or since one leads lags light travel separating sites, offsets map system geometry. 44-minute source shows no such offset radio and X-ray pulses since measurement precision, radio on, X-ray on, radio peaks, X-ray peaks. Radio fades, X-ray fades, near perfect correlation. Phase lock tells scientists crucial radio and X-ray emissions originate same region or same particle population, cannot independent processes different system parts. Whatever mechanism births one births both. Some physics processes birth both concurrently. Synchrotron radiation 1. Electrons accelerating magnetic fields near light speed emit broad spectrum radiation. Lower energy electrons radio waves, higher energy X-rays. Single electron population spanning energy range naturally yields both emissions. For work, need strong fields and efficient particle acceleration. Electrons reach least 10 billion electron volts, birth observed X-rays, demands powerful accelerators, perhaps field interactions, or shocks plasma streams colliding. Radio to X-ray brightness ratio clues electron energy distribution, source brighter radio than X-ray, suggesting most electrons moderate energy, small fraction reaching high energy X-ray production. Fits many acceleration mechanisms, energy dropping higher energy particle numbers. Variability models fit 2 months radio dimming, corresponding X-ray dimming, to ratio near constant. Coordinated fading strengthens common origin idea. If different mechanisms, expect independent dimming. High radio polarization indicates fields ordering emission. X-rays less polarized expected. X-ray polarization hard produce and measure, but detectable faint X-ray polarization aligning radio direction. Another common origin sign. Shorter timescales show correlation to 2 minutes. Radio and X-ray intensities fluctuate second by second. Subpulse variations match wavelengths. Radio brightness spikes. X-ray brightness spikes moments later. Slight delay perhaps, light travel across emission region, or projection effect. Coordination degree demands physical link to unrelated processes, cannot accidentally perfect sync long. 44-minute clock drives both emissions. 2-minute window affects both. Monthly fading affects both to manifestations. Same fundamental phenomenon. But what phenomenon? Particle spiraling fields explain basic physics, but what births those fields, accelerates those particles, sets 44-minute cycle. Phase lock answers some questions, raising others, but definitively excludes models radio and X-ray different components. Any theory proposing radio, one binary star X-ray other immediately ruled out. Models radio jets, X-ray accretion disk face severe challenges. Emissions bound to tightly. Constraint eliminates many possibilities. Narrows viable explanations, but points no single model. Magnetar births phase locked emission. White dwarf binary 2. Other strange scenarios too. Phase lock necessary understands source, but insufficient identify. What astronomers need more data, more observations, more wavelengths. Optical spectra identify companions. Infrared detect thermal emission. Gamma ray monitoring check higher energy emissions. Each new datum constrains models further. The gathering requires worldwide telescope coordination. Each competing time demands and requires source continue pulsing, source fading or dying before eyes initial detection, follow-up 6 months later. Both radio and X-ray emissions drop substantially. Source not switched off, but markedly dimmer. 44-minute period continues unchanged, but pulse amplitude fraction initial strength. Behavior unusual long period transients. Some LPTs observe just relative stable brightness. Others appear weeks or months, then vanish forever. This claims middle ground fading, not abrupt blink. Some explanations possible dimming perhaps, emission mechanism running fuel, if self-powered stored magnetic or rotational energy. Reservoirs deplete like draining battery. Source produces less light reserves dwindle. Alternatively, geometry changing if seeing pulses specific structure sweeping view and structure processing or wobbling. gradually misaligning Earth. Observe dimming beam grazing larger margins. Eventually miss entirely source vanishing view, though continuing emit. Another environmental perhaps source, traversing denser gas region. Interactions disrupting emission mechanism, or gas absorbing some radiation en route. Though unlikely radio and X-rays penetrate gas well, and expect different wavelengths affected differently, not observations show. Binary orbital evolution explain dimming if white dwarf pair losing angular momentum or orbit shrinking. Magnetic interaction geometry changing, perhaps shrinking orbit transitioning system active to quiescent state. Perhaps witnessing final phases pre-indetectability. Coordinated radio X-ray dimming argues against simple absorption, or geometry both wavelengths fading proportionally maintaining relative brightness. Suggests emission mechanism weakening itself, not radiation blocked or beam missing. Months-long changes common many astronomical objects young stars flare, and fade accretion rates fluctuate. Variable pulsars regular cycles varying amplitude. Active galactic nuclei brighten and dim years. 44-minute source joins changeable phenomena cast, but long-period transients, presume stable regular pulses steady brightness long. Fading challenges assumption perhaps, LPTs inherently variable, life cycle perhaps flare bright years, then fade darkness. If so, astronomers face detection challenge these objects spend most existence dim or dormant, occasionally brightening detectable. Subsequent surveys underestimate true population, catching only active phase ones. Galaxy may harbor hundreds or thousands inactive LPTs invisible current instruments. Dimming impacts future observations too if trend continues. Source to faint detailed study years. Researchers limited window gather data pre-dropping detection threshold. Urgency spurred telescope proposal flurry everyone observing well can. Some telescopes to sensitive detect source anymore Chandra, small collecting area, barely sees X-rays. Long exposures needed enough photons analyze. Larger dish radio telescopes still detect clearly, but even signal to noise worsened. If source vanishes completely, may return years or decades later. Some LPTs show this first discovered gleam J1832-0911 visible 3 months then gone. Unseen since, perhaps 44-minute source follows similar, or fades low stable brightness, still pulsing, but nearly undetectable. Future telescopes sensitive current gear rediscover, and study quiescent phase. Understanding active and quiescent illuminate controlling physics. Currently astronomers monitor, tracking fade, measurements while possible, wondering witnessing temporary fluctuation, or one-way silence journey. Australian square kilometre array pathfinder telescope sees more sky most year Western Australia Waiari country. ASKAP 36 dishes spread 6 kilometers red desert, each 12 meters, diameter relatively small radio astronomy standards, but operating interferometer, combining all dish signals achieving much larger telescope resolution, while maintaining wide field view. Field key most radio telescopes, see sky patches fraction degree. ASKAP observes 30 square degrees simultaneously about 150 full moons side by side. Allows rapid broad area surveys ideal transients and variable hunting. Enabling technology phased array feeds traditional radio telescopes, single receiver dish focus. ASKAP uses receiver arrays essentially multiple radio cameras per dish. Back-end electronics combine signals, multiple beams observing directions simultaneously, one telescope, becoming many. Design philosophy reflects broader radio astronomy trend survey. Focus strata, pointing known interesting objects. Modern telescopes systematically scan skies, seeking unknown phenomena. ASKAP embodies approach radio imaging broad sky swaths, then processing data anything anomalous. 44-minute source surfaced, such survey ASKAP conducting fast project fast and slow transients, and variability survey designed find objects changing minute to day timescales. Telescope repeatedly images same sky regions comparing observations detect changes. Most sky stable stars not flicker noticeably. Galaxies not brighten, but occasionally something new appears supernova exploding, star flaring, Black hole activating. ASKAP galaxies. Cataloging dynamic universe. Data processing demands complex software. Millions sources fill each image. Automated algorithms compare observations days or weeks apart. Flagging changes. Candidate list. Then human astronomers reviewing interesting cases, deciding follow-ups. 44-minute source not appear. Stable object vanishes between observations. On-off behavior caught attention immediately. Deeper analysis revealed periodic pattern. Knowing period. Researchers folded data, stacking multiple cycles, boosting signal. Source sharpen focus. ASKAP remote site minimizes radio interference. Absent cell towers. Distant broadcasts. Few power lines. Radio quietness allows faint signal detection. Drowned urban areas. Australian government legally protects site, restricting emissions. Large exclusion zone. Telescope operates robotic. Urban astronomers, hundreds kilometers away. Remote control. Programming observations. Monitoring performance. Data streams. Computer clusters. Immediate processing. Hours post-observation. Processed images. Analysis ready. Each ASKAP dish operates independently or array part. Flexibility allowing simultaneous projects. Some dishes pulsar observing, while others map hydrogen gas. Others hunt transients. Multitasking maximizes science yield. Design precursor. Square kilometer array. Future telescope 50 times sensitive. ASKAP Pathfinder. Testing technology. Observation strategies. Lessons inform larger instrument building. Discovering 44-minute source validates survey approach. Proves wide field monitoring value. If not ASKAP unique capability. Source undetected years. Traditional telescopes targeting known objects never notice pulsing signal. Unthought observation area. Only serendipitous survey telescope stumbling it and random coincidence bringing X-ray discovery. Chandra X-ray Observatory not seeking radio source finding it. Launched 1999. Chandra Earth orbiting elliptical path. 65 hours complete. Apogee. Telescope reaches 130,000 kilometers. Altitude 1/3 moon distance. High orbit places Chandra above radiation belts. Noisy sensitive detectors. X-ray astronomy. Space only. Earth atmosphere blocks X-rays, shielding harmful solar radiation. For ground barring X-ray telescopes. Satellites like Chandra Solway observe electromagnetic spectrum part. Chandra bears mirrors. Unlike optical telescopes, X-rays not reflect surfaces like visible light, penetrating most materials. Focusing X-rays uses grazing incidence. Mirrors shallow angles. X-rays glancing off, glancing not penetrating. Chandra mirrors nested cylinders. Polished atomic smoothness. Telescope small field view typically under half-degree wide. Trade-off sharp resolution and sensitivity. Chandra images detailed small areas, not broad surveys. Deep individual object studies, not wide swaths. Discovery day 44-minute source. Chandra observing supernova remnant S and J1832.7 to 0.2 expanding debris cloud. Exploded massive star perhaps 20,000 years ago. Remnants say Milky Way region. Radio source pure coincidence. Observations span hours far exceeding 44-minute cycle. INTERIM. Radio source pulse multiple times. Chandra logged arriving X-ray photons every 44 minutes. Though initial supernova remnant data analysts focused expanding gas clouds, not point sources. Link emerged post-radio team coordinate announcement. Mysterious pulsar. Comparing coordinates. Archive Chandra observations. Spatial overlap discovered. Retrieving data. Timing analysis. Pulses clear. Serendipitous find changed everything. Pre-radio source interesting, but not unique. Post. Sol long period transient X-ray detected. Uniqueness elevates curiosity. Extreme importance. Chandra sensitivity enabling visual detection. Despite faintness X-ray flux view 10 to -14 erg/second per square centimeter translating about 1 photon detected every few seconds. Active phases. Long observations and careful analysis needed. Tease faint signals. Background noise. Chandra timing precision. Superb. Each photon time-stamped. Better millisecond accuracy. Allows astronomers measure 44-minute cycle, confirm X-ray pulses, exactly align radio pulses. Sans timing precision, correlation missed, post-discovery. Chandra additional source observations each confirming 44-minute period. Also tracked months-long fading X-rays dimming radio emission pace, maintaining brightness ratio. Follow-up observations competitive Chandra, oversubscribed proposals, exceeding available hours. Convincing review committees award time, demands strong scientific justification. Uniqueness helps, Sol X-ray emitting LPT essential observe while detectable. Collected data are not just timing and brightness, but spectral information revealing X-ray temperature composition emission regions. Source spectrum soft most photons relatively low energy, reasonably fits models hot plasma 10 million Kelvin, or non-thermal accelerated particles. Different spectral models, different emission mechanisms. Thermal suggests gas-heated shocks, or magnetic reconnections. Non-thermal implies particle acceleration, synchrotron electron spiraling fields. Data not clearly distinguished, leaving room multiple interpretations. What Chandra definitively proves high-energy processes operating source whatever births radio creates X-rays via intense mechanisms. Not quiet audity this particle acceleration engine, and magnetic interactions extreme conditions. All because the telescopes accidentally same spot same time. Required field strengths explaining source approach matter sustainment limits magnetic fields invisible, but potent, guiding charged particles, storing energy shaping compact object environs. Daily life, fridge magnets generate 100 Gauss fields, Earth's surface half Gauss these tiny astronomical physics standards. Sunspots contain few thousand Gauss, fields strong enough significantly affect plasma motion energy flows. White dwarfs typically fields 0 to million Gauss, though rare examples 100 million Gauss plus. Neutron stars extreme typical trillion Gauss. Magnetars quadrillion, birthing observed radio and X-ray brightness with traits. Theoretical models require fields 100 million to billion Gauss. Uncomfortable zone to strong typical white dwarfs, to weak neutron stars boundary between regimes. If source white dwarf, ranks strongest magnetic white dwarfs found. Over 100 million Gauss fields, extremely rare white dwarfs. Current theories struggle explain strong field acquisition. Perhaps inherit massive progenitor stars, perhaps field amplification merger events to white dwarfs colliding. Both scenarios poorly understood. If source neutron star, field surprisingly weak, even old neutron stars, retain least billion Gauss. Fields below threshold indicate extreme age hundreds thousands to millions years, but such ancient neutron stars inactive. Fields decayed unable efficiently accelerate particles. Required field strength depends geometry emission mechanism if radio synchrotron. Charged particles spiral field relativistic speeds. Tighter spirals higher energy particles higher frequency radiation. Birthing both radio and X-rays same particle population. Demands strong fields efficient acceleration. Magnetic energy density huge in billion Gauss field. Stored energy per cubic centimeter exceeds matter rest mass energy ordinary densities. Field dominates environment physics. Particles cannot free move must follow field lines. Gas cannot flow perpendicular fields, but along. Such strong fields affect atoms themselves. Electrons cannot orbit nuclei normally. Forced elongated orbits field aligned. Energy levels shift, altering atom absorption emission light. Spectra become bizarre features wavelengths absent weak fields. Birthing such fields requires compression, or dynamo action compression stellar collapse. Radius shrinking flux conservation, forcing field intensification. Modest field star spread volume, becoming compact high intensity field concentrated small region. Dynamo action liquid motion birthing field stellar interiors convection, or accretion disk turbulence amplifying weak field strong, but sustaining 100 million Gauss plus demands specific hard achieve maintain conditions. Field stability issue 2 magnetic energy releasable reconnection. Field lines breaking reforming lower energy configurations. Reconnection heats plasma accelerates particles exactly source seeming doing, but repeated reconnection ultimately dissipates field, unless mechanism continuously regenerates. If source binary, Interobject magnetic interactions, sustained field strength, tidal forces stretching field lines, orbital motion generating currents, amplifying field, companion supplying new flux via own field or in falling plasma. All considerations make magnetic field problem. Central understanding source wrong field strength, nothing else works. To weak cannot birth observable emission, to strong predict unobserved phenomena. Field must narrow range, and range corresponds rare extreme objects. Nature excels extremes, but extremes always rare, whatever source. Occupies magnetic field strength regime. Few objects inhabit alone. Indicates seeing something unusual, perhaps transitional or revolutionary endpoint, reach fraction compact objects. Field alone not answers, just puzzle piece larger jigsaw. Power must come somewhere, and source burns alarming rate in 2-minute active phase. Object emits 10 to 32 UG/second radio alone. At X-rays push higher. Sustaining millions years every 44 minutes ceaseless. Demands astonishing total energy budget. Simply put, our sun produces about 4 times 10 to 23 UG/second all wavelengths. Source, much smaller. Short bursts matches substantial sun fraction radio and X-rays alone. Energy whence? Some natural reservoirs exist. Rotation 1. Spinning object stores kinetic energy, slowing friction or radiation, converting other forms. Pulsars tap rotational energy, gradually slowing millions years, broadcasting radio space. But 44-minute neutron star, comparatively little rotational energy versus fast pulsars. Stored energy scale spin speed squared, having speed loses 3/4 energy. 44-minute spinner, less millionth rotational energy, second pulsar same mass radius. Reservoir depletes quickly, emitting 10 to 32 UG/second. Simple calculations show source exhaust rotational energy years, not millions seeming existence requires, or source extremely young catching mid-short active phase, or spin not primary power. Magnetic fields store energy to strong field, compressed energy awaiting release. Magnetars power spectacular bursts, tapping magnetic energy field lines, twisting, reconnecting, heating plasma, accelerating particles. For a 44-minute source, 100 million Gauss field 10 km region. Calculable stored magnetic energy about 10-40-7 UGs. Sounds much, but 10 to 32 UG/second. Source drains reservoir 300,000 years, perhaps long enough, but only field not regenerating. Gravitational potential another option in binaries. Matter falling one star another. Gravity converting potential kinetic and heat. Powers many bright galactic X-ray sources. White dwarf binary losing mass one component, other easily powers observed emission. White dwarf gravity well deep in falling material surface, releasing tremendous energy, depending mass transfer rate. Such systems shine millions years, exhausting donor star. But observed emission traits not fully match typical accretion systems. Radio brightness and X-ray coordination suggest beyond simple accretion. Perhaps accretion powers system, but magnetic interaction shape emission. Perhaps combination multiple energy sources contributing. Tidal energy orbital interactions. Roll 2 as two objects orbit closely. Raise tides each other. Tides dissipate energy, friction heating interiors. Close binaries lose orbital energy way, slowly spiraling in. 44-minute orbital if cycle represents places objects very close. Tidal interaction strong. Energy dissipation could power emission. However, tidal heating usually births thermal radiation, infrared warm surfaces. Efficiently converting infrared radio and X-rays requires additional steps. Perhaps answer involves multiple mechanisms working together. Orbital energy sustained system. Magnetic fields channel convert energy. Spin modulates emission. Each component contributes, none sufficient alone, but together providing source needs. Or perhaps source inherently transient, destined shine briefly fade. Many astronomical phenomena, temporary supernovae explode once, fade months. Novae flare, fade years. Perhaps long period transients, class temporary events, blazing decades or centuries, then darkening. If so, fortunate observing mid-active phase most dark, Light shows ended, or not begun. Galaxy may harbor thousands long-period transients, formerly silent invisible. Energy budget unsolved definitively. Every proposed model faces challenges, explaining power source and maintenance. Source broadcasts indifferently theoretical difficulties. Source resides crowded neighborhood star's birth and dicosmic drama 15,000 light-years Earth places Milky Way disk. Flat region most stars inhabit. Galaxy 100,000 light-years diameter. So object in a regions near a galactic center than edge. Specifically, lies Scutum constellation Earth, view Scutum unremarkable night sky. Small southern celestial equator constellation often lost Milky Way glow, but occupies key direction towards Scutum Centaurus arm. Spiral structures giving galaxy pinwheel shape. Spiral arms not solid structures, but density waves regions stars and gas clouds temporarily bunch orbiting galactic center. Star formation prioritizes spiral arms increased density triggering gravitational collapse gas clouds. Short-lived bright massive stars illuminate arms, making invisible light brilliant. 44-minute source such region surrounding stellar nurseries stars forming now. Massive giants brief bright lives exploding supernovae millions years. Remnants scattered area expanding gas, dust shells enriched, heavy elements stellar cores forged. Environment dusty 2 microscopic particle clouds, blocking visible light complicating optical astronomy. Infrared and radio observations penetrate better wide radio telescopes, like ASKAP essential studying objects this direction. Visible light telescopes see only obscuring haze. Galactic coordinates place, source 22.7 longitude 0.2 latitude longitude, angular distance, around galactic center, latitude height above or below galactic plane. 0.2 degrees means source nearly exactly plane embedded densest disk stars. Position meaningful source origin and evolution galactic plane objects tend younger plane above or below. Old stars time drift plane gravitational interactions. Source plane residence suggests relatively young perhaps millions or tens millions years not billions. However compact objects remain plane even old, if not kicked much birth. Neutron stars usually supernova blasts, ejecting plane high speeds. White dwarfs no such kicks drift slowly. If 44-minute source white dwarf binary. Plane position unsurprising regardless age. Distance measurements from several indicators radio wave dispersion estimates. Are ADIO waves traversing interstellar plasma? Different frequencies arrive slightly different times. Dispersion amount depends intervening plasma quantity. Correlating distance. Galactic plasma distribution model converts dispersion distance. X-ray absorption another clue gas and dust source preferentially absorbing soft X-rays. Absorption amount visible X-ray spectrum constraining material column density, a long line sight. Combined galactic structure maps. Yields distance estimate. Both methods agree 15,000 light-years. Uncertainty perhaps 20% source closer 12,000 or farther 20,000. Better distance measurements require parallax observing source apparent position shift Earth orbiting Sun. Demands precise position measurements years. Knowing distance allows luminosity calculation total output energy. Brightness tells light reaching Earth. Luminosity source actually produces how much light. Difference crucial physics, understanding near faint object appear bright distant bright one. Source outputs among highest long period transients produce brightest known examples. Makes essentially stronger others, or oriented emission beam nearly usward. Position determines observable telescopes, southern hemisphere observatories see clearly. Northern telescopes struggle never rising high horizons. Geographic limit means many world largest telescopes cannot contribute observations work Australian, South African, South American facilities. But knowing where not telling what. Every astronomy textbook revision needed. If source represents new stellar death phase, we thought understood stars end sun like small stars swell red giants. Shed outer layers leaving cooling white dwarf core billions years. Massive stars explode supernovae leaving neutron stars, or black holes. Taxonomy seemed complete mapped life cycle birth to death every mass stars. Long period transients, show missed something, represent behaviors unpredicted, standard stellar evolution models, or witnessing rare cases, unusual circumstances yielding surprises, or overlooked entire phase, all certain mass stars pass. If 44 minutes saw old magnetar, seeing neutron star evolution, far beyond theory end. Magnetars presumed young objects, potent fields birthing fireworks thousands years, then fading darkness. Finding still active hundreds thousands years, means magnetars live longer predicted. Why theory wrong? Perhaps field decay more complex. Simple models suggest, perhaps fields not monotonically decay, but cycle weakening regenerating. Perhaps crustal rearrangements, aging neutron stars, occasionally reactivate dormant fields. Observe only 30 magnetars, not enough. Map full life cycle. If source white dwarf binary, seeing magnetic interactions, binaries birthing previously unimaginable phenomena. White dwarf binaries, common galaxy harbors millions, but fractions show long period transient behavior. What makes special? Perhaps only binaries, ultra strong fields, and precise orbital configurations birth detectable emission. Narrow parameter space, orbital cycle slightly off, nothing interesting happens. Fields slightly weaker, emission drops detection. Most white dwarf binaries boring, select few become cosmic lighthouses. Precedent, not all neutron stars become pulsars, only favorable field and spin axis birthing Earth-directed beams. Similarly, not all white dwarf binaries become long period transients, only meeting specific criteria birth spectacular periodic emission. Observe stellar evolution sensitive binary interactions, most stars for multiples. Companions profoundly influence evolution, strip mass each other, catastrophically merge, exchange angular momentum, altering spins. Many phenomena once attributed single stars, actually binary evolution products. 44-minute source may scream, rethink binary evolution, perhaps systems pass long period transient phase, standard evolutionary step. Every suitable white dwarf binary someday, one we see examples, if true. Galaxy full protocyclic transients, future activating systems, and post-active long period transients. Discovering inactive examples provides crucial context. Common, show long signature, even quiet. Theoretical astrophysicists racing incorporate long period transient stellar evolution codes. Computer programs simulate star life cycles, tracking changes millions years. Adding new phases requires understanding, controlling physics understanding incomplete. Few researchers propose entirely new object classes, perhaps supermagnetized white dwarfs, separate category, just strong field white dwarfs, but fundamentally different objects formed. Special circumstances, perhaps neutron white dwarf binary systems, both compact types birthing long period transient emission magnetic interactions. Each new idea births predictions if new class exists. Find examples, specific traits. If specific formation pathways birth long period transients, see them star clusters, certain ages, or metallicity regions. Testing predictions requires surveys. Impact beyond compact objects, understanding stellar death improves galactic chemical evolution knowledge. Dying stars enrich interstellar gas heavy elements. Enrichment mechanism depends remnant type formed, and evolution way. Wrong late stages, wrong element sources. Best science and expected observation forces. Rethink established models. Models evolve, fit new data. Predictions emerge. Tests occur. Understanding deepens. 44-minute source teacher revealing knowledge gaps unknown existed. But full integration discovery, grand stellar evolution story, years work. Strange object curiosity. 10 pattern. 100 rules. Astronomers systematically hunting additional long period transients. Goal, building large enough sample, statistical studies feasible. 10 examples, each unique, 100 or 1000. Map full diversity, identify subtypes. Some telescopes dedicated allocating time search. ASKAP continues broad surveys, imaging wide sky regions repeatedly. South African meerkat sensitive ASKAP conducts similar southern sky surveys. Canadian CHIME continuously monitors northern skies. Surveys generate massive data volumes, millions sources each observation. Software algorithms compare images days or weeks apart, identifying changes. Most changes instrumental artifacts, or distant active galactic nuclei fluctuating. Sifting false positives, true transients labor-intensive. Machine learning helps neural networks
Quantum
train known
entanglement
transients,
linker
recognize
connects
similar
qubits
signals,
across
new data.
dimensions.
Flag candidates human review. Process imperfect, but accelerates discovery systems years, manual find months. Initial results suggest long-period transients commoner initial thought first few discoveries seemed rare luck, but improving search sensitivity and sky coverage. More candidates emerge, some steady pulsing, others intermittent appearing. Diversity suggests multiple populations, not all long-period transients emit X-rays. 44-minute source traits perhaps anomalous. Follow-up X-ray observations, other LPTs detect nothing or X-ray emission much weaker, or produce radio via the non-accompanying X-ray mechanisms. Raises questions 44-minute source representativeness perhaps, extreme example. Brighter and more energetic typical LPT. Theories based it misleading, if most long-period transients qualitatively different. More multi-wavelength discoveries needed. OPTICAL identification forward path if researchers precisely identify optical counterparts binary companions spectroscopy possible. Spectroscopy reveals chemical composition, temperature, velocity definitively identifying white dwarf or red dwarf or other types. To LPT's optical counterparts, GLEAMXJ of an 04 to 37 and ILTJ 1101 plus 5521, both tied binaries, white dwarfs, unlow mass stars. Spectra confirm links. Cases prove least some LPTs white dwarf binary related, but extrapolating to examples all long period transients risky perhaps, subset white dwarf related, others solitary magnetars or unimagined oddities. 44-minute source no confirmed optical counterpart crowded environment complicating identification. Many stars same sky patch, which if any related. Higher resolution imaging results Hubble Space Telescope or upcoming ground extremely large telescopes separate individual stars field. If one shows variability or odd colors, prime spectroscopy candidate. Growing sample distance measurements illuminate distribution concentrated galactic plane or scattered galaxy-wide. Young or old star populations associated, central or evenly spread galaxy. Each distribution pattern implies different formation mechanisms. 44-minute source galactic plane suggests relative youth or dense star-forming birth. If most LPTs share trait, points binary interaction scenarios crowded environments. If others widely dispersed, formation mechanism not requiring specific environment. Population statistics constrain theories too, of long-period transients number thousands galaxy, must form relatively common progenitors, if hundreds, require special circumstances. Current estimates suggest galaxy harbor 1,000 to 10,000 detectable LPTs. Current technology many exist, but to faint observe. Implies whatever births long-period transients, not extremely rare perhaps 10% white dwarf binaries, pass LPT phase. Perhaps all magnetars certain initial field strength evolve LPTs given time. Progenitor population must large, finding more examples not academic exercise path understanding. Each new discovery constrains theories, each period, brightness, spectrum or polarization measurements, narrows parameter space. Eventually single explanation fitting all observations, search continues. To objects locked mutual orbit birth complex physics single stars never experience. Imagine white dwarf and red dwarf orbiting every 44 minutes orbital separation about 800,000 kilometers less double sun diameter. Distance. Gravity dominates. Each star raises massive tides other. Earth tides bulge oceans moon gravity pull. Stellar tides similarly deform shapes. Closer stars, stronger tides, 44-minute binary. Tidal forces extreme stars elongating toward each other egg-shaped, not spherical. Tidal bulges rotating stars, but not quite synchronous orbit. Friction bulge and star rest dissipates energy. Energy from orbital motion orbit gradually shrinks. Period decreases millions years. Stars spiral merger. Process called tidal locking timescale, much shorter stellar ages. Each star spin synchronizes, orbital cycle same face, always companion ward. Moon always showing Earth same face, 44-minute binary. Accurate model, both stars rotate once 44 minutes. But tidal locking whole story, not magnetic white dwarf 100 million Gauss strong field. Field extends far beyond surfaces, filling interobject gap. Companion star, or outflowing material traversing field. Conducting material crossing field lines, experiences drag field, exerts forces, charge gas particles, forces channel gas. Flowing field lines not freely. Matter spiraling white dwarf, cannot fall straight surface, must follow field-defined helical paths. Creates hotspots, field lines connecting white dwarf surface. Material channel field lines, slamming hotspots, heating millions degrees. Hotspots emit X-rays. White dwarf rotating. Hotspots sweeping in out view, birthing periodic X-ray emission. Radio possibly different region, perhaps particle acceleration field, interacting in falling companion gas. Field reconnections, field lines breaking, reforming, releasing energy, accelerating electrons, near light speed. Electrons spiraling, remaining field, emitting synchrotron radiation. System geometry determines seeing and when, if radio emission beamed lighthouse. Detect only beam sweeping Earth, beam wide. Lasting 2 minutes, crossing view 42 minutes, darkness pointing elsewhere. 2-minute duration, also reflecting emission region, visibility time, perhaps magnetic interactions continuous. But see specific structures, rotating view. Imagine emission curtain, field aligned, see curtain face on. Nothing edge or back turned. Orbital dynamics explain long-term changes. To orbital precession, wobbling top-like. Orbital plane tilting, months or years, tilting. Viewing angle, system changes. Beam sweeping less directly us, causing observed dimming. Eccentricity adds wrinkle, most close binaries circular orbits, but some retain elliptical, eccentric orbit. Star distances vary, cycle close. Interactions strengthen. Far, weaken. Modulating emission intensity, orbital timescale. If 44 minutes source truly binary, both objects influence motion, orbiting common center mass. More massive moves less, less massive more. Precise orbital measurements reveal mass ratio, determining binary stars to white dwarfs, white dwarf and red dwarf, or other combination. Such measurements require years monitoring. Doppler shift spectral lines reveal orbital velocities. Sky position changes, if measurable, show direct orbital motion. Thus far insufficient data. 44-minute source, future observations provide needed precision. Binary evolution predicts endpoint, eventually orbit shrinks enough stars merge. White dwarf binaries, merger possibly supernova, or birthing massive white dwarf. White dwarf red dwarf system. Red dwarf possibly shredded entirely, leaving white dwarf debris disk surrounded. How long until happens? Gravitational wave emission and tidal friction both dissipate orbital energy. Time scale depends. Mass separation, 44-minute orbit. Preliminary estimates suggest millions years remaining pre-merger. Witnessing midlife system, not final moments. Understanding binary dynamics, essential source. Understanding every orbital mechanics. A magnetic interaction detail contributes observed emission. Interconnected complex system where everything affects everything else. Converting stored energy, radio and X-rays require specific physics processes. Synchrotron radiation leading candidate. Electron spiraling, magnetic fields, relativistic speeds, emitting photons. Emission frequency depending electron energy and field strength. Low energy electrons, radio waves. High energy X-rays, population spanning energy range, naturally birthing both. Mathematics well understood. Full relativistic gamma energy electron, traversing strength B field, calculable output power and frequency spectrum. Synchrotron emission, common astrophysics powers, radio galaxies, planetary nebulae, supernova remnants. Applying here straightforward, but conditions met. First, relativistic electron supply, something accelerating least 10 billion electron volts X-rays. Second, strong magnetic field, tight enough electron spirals, efficient radiation. Third, emission beam geometry, earthward, Magnetic reconnection, plausible acceleration mechanism, oppositely directed field lines, colliding, breaking, reconnecting, lower energy configuration. Released energy, heating plasma, accelerating particles. Reconnection occurs, solar flares, Earth magnetosphere, perhaps many astrophysical contexts. 44-minute source. Reconnection, white dwarf field, interacting companion plasma field lines, anchored white dwarf clashing in falling gas fields. Reconnecting, launching high-energy electrons, electron spiraling, remaining field emitting synchrotron. Reconnection rate, determining emission brightness, faster reconnection, more particles accelerated. Brighter emission, slower reconnection, fainter. If reconnection rate, time varying, perhaps companion mass flow fluctuations observed, brightness variations explained. Cyclotron emission, alternative electrons, circling magnetic fields emitting cyclotron frequency, specific frequency, field strength, and electron charge to mass ratio. 100 million Gauss field. Cyclotron frequency, radio range, harmonics, birthing emission, multiple frequencies simultaneously. -1 cyclotron, usually weaker synchrotron, relativistic particles, dominates moderate energy electrons, not extreme X-ray production. Synchrotron, better overall spectrum explanation. Curvature radiation possibility, particles, curving magnetic field lines, emitting photons, even sand spiraling. Field line curvature, forcing particle acceleration, charged radiation. Process key pulsar magnetospheres. 44-minute source. If particles, flowing field lines, companion to white dwarf, curvature radiation contributing emission, but like cyclotron, usually narrower spectrum than observed. Synchrotron, flexible explanation. Thermal emission, birthing X-rays, if in falling white dwarf material, heating tens millions degrees, emitting thermal X-rays, spectrum, blackbody, or modified depending optical depth. Observations fit possibility. But thermal emission struggles, radio components, hot thermal plasma, they're efficiently producing radio. Needs separate radio mechanism, but phase lock implies not. Why non-thermal processes like synchrotron preferred? Coherent emission mechanisms exist, but unlikely. For example, Jupiter amplifies radio-stimulated emission, birthing narrow, extremely bright signals. Pulsars use maser-like processes, achieving anomalous brightness temperatures. But coherent mechanisms hard sustain broad frequency range, long durations. Emission geometry issue 2. If beamed, small sky fraction receives photons, Earth beam path detect anything. Beam naturally birthing periodic emission, rotating or orbiting systems, beam sweeping Earth seeing pulses. Beaming factor large if beam covers 1% sky, detect 100 such systems, galaxy harbor thousands similar objects, all beaming away as invisible telescopes. Increases true population versus observed numbers substantially. Alternatively, emission not beamed, but modulated absorption, or line of sight, perhaps always receiving source radiation, but surrounding material blocking part-time structures, rotating or precessing, moving in out view, birthing apparent pulses. Absorption model trouble explaining sharp on-off gradual column density changes, birth gradual brightness changes, not observed abrupt switches, unless absorbing material sharp edge slicing emission knife-like. Absorption seems insufficient. Multiple mechanisms, possibly concurrent synchrotron, major emission, thermal contributing X-rays, beam geometry shaping Earth reaching, full picture likely complex, involving several processes, teamwork. Distinguishing scenarios requires detailed observation, spectra show thermal versus non-thermal, polarization measurements map field structure, timing studies track short timescale changes, each observation another clue. Emission mechanism not academic question determines constraining physics, right mechanism, everything else slots place, wrong, and confusion persists. Sky. Source appears supernova debris wreck, but appearances deceive. Supernova remnant S and J1832 to 0.2 appears faint, expanding gas shell fragments, massive star exploded, perhaps 20,000 years ago. Shock waves blast, continuing plow surrounding gas, heating millions degrees, accelerating cosmic ray particles. Supernova remnants often contain neutron stars, or black holes collapse, leftovers star exploded. Finding pulsing object remnant seems natural explosion birthed neutron star. Neutron star now signaling radio and X-rays. Case closed, but careful analysis shows link coincidental. Source and remnants appear close from view, like to buildings touching distant view, but actually different streets. Source and remnant possibly different distances, same line sight. Remnant distance estimates, shockwave expansion models, and gas density plowing estimates place about 10,000 light-years, plus or minus few thousand. 44-minute source-based radio dispersion and X-ray absorption 15,000 light-years, 6,000 light-years apart, double sun diameter. Unrelated, one behind other view. Accidentally sky-aligned. Other factors argue against association. First, supernova remnants fade time. After 20,000 years, most barely detectable, this faint fitting expected age, but neutron star-born supernova young, energetic, fast-spinning, bright. 44-minute source slow-acting old object ages mismatch. Second, supernova-born neutron stars usually kicked asymmetric explosions, hundreds km/second speeds. Kicks eject neutron stars' birth sites. 20,000 years, 300 km/second. Carries neutron star over 6 light-years remnant center. 44-minute source shows no clear offset remnant center, but distance uncertainty not proof. Third, if source-born supernova show chemical enrichment explosion, supernovae produce heavy elements, mixed remnants. Companion star remnant show traces element spectrum. No optical identification. 44-minute source, yet so test undone. View coincidences not rare, galaxy thousands supernova remnants and thousands compact objects. Both populations spread galactic disk. Alignment chances frequent. Assuming connection sans confirmation leads error. Not meaning impossible, perhaps source related supernova just unclear. Perhaps white dwarf runaway coincidentally passing remnant region. Perhaps supernova shock triggered something pre-existing, binary activating long period transient behavior. Or remnant much closer, estimated same distance source. Distance measurements uncertain, remnant evolution models assumptions possibly wrong. Additional observations refine remnant distance, bringing to objects physically nearer. Chandra initial observations targeted supernova remnant, not 44-minute source remnant interest target. Discovering pulsing source serendipity. Coincidence enabled discovery, but creates selection bias, no source, because coincidentally remnant field. How many other LPTs lurk unmapped regions? Untangling true links, random coincidences, requires multiple evidence lines, distance measurements agree, ages match, chemical compositions show connection, kinematic properties like velocities consistent. For 44-minute source and supernova remnant, most tests yet undone. Future observations resolve question. Proper motion measurements tracking source sky motion years. Reveal moving remnant center expected kick. Optical counterpart spectrum detects supernova enrichment. Refined distance estimates confirm or exclude physical link. Currently consensus leans random coincidence, source likely foreground, or background accidentally aligning remnant. Nature frequently plays tricks, reminding astronomers, seeing not always believing. Next generation telescopes resolve this mystery or discover 10 like it. Construction underway. Square kilometer array or SKA radio telescope, 50 times sensitive current instruments, split Australian and South African sites, comprising thousands antennas operating giant single tool, completing early 2030s. SKA detects now invisible faint radio sources. Long period transients. Key science goal: SK conduct deep surveys, monitoring million sources changes. Sensitivity revealed 10 times fainter LPTs than 44-minute source. If common, SKA find hundreds or thousands, if rare. Least detect brightest examples galaxy-wide, even nearby galaxies. Larger sample transform, understanding with hundreds examples. Astronomers measure period, brightness, polarization, spectral properties, distributions, identify subtypes, track correlations. Test theories, statistical rigor, not single object arguments. X-ray astronomy advancing to next-generation X-ray observatories, planned 2030s. Advanced X-ray imaging satellite, or AXIS combines Chandra-sharp vision decollecting area fainter sources. European New Athena mission conducts wide-field surveys, while providing spectroscopy capabilities. Telescopes systematically hunt X-ray emission, known radio LPTs, if 44-minute source typical. Others emit X-rays too. If unique, uniqueness informative, either way. Coordinated radio and X-ray surveys provide needed multi-wavelength data, constrain emission mechanisms. Optical astronomy contributes spectroscopy. Chilean, extremely large telescopes, building 39-meter mirrors, dwarfing current facilities. Light gathering power and resolution enable spectroscopy faint optical counterparts crowded fields. LPT binary companions identified and characterized. Infrared observations complement optical James Webb Space Telescope operational detect cool stars and warm dust visible telescopes miss. If long-period transients involve red dwarf companions or dust disks surrounded. Webb sees spectroscopy capabilities reveal molecular features, diagnosing star types. Gravitational wave detectors evolving to space laser interferometer space antenna, or LISA launching early 2030s. Unlike ground detectors sensing high-frequency waves, black hole and neutron star mergers, LISA detects low-frequency waves, white dwarf binary systems. If long-period transients close white dwarf pairs, orbital motions birth gravitational waves, LISA detect directly, precisely measuring masses and orbital parameters. Gravitational wave signals combined electromagnetic observations confirm systems and test general relativity strong field regimes. Any deviation, even slight, revolutionary. Alternative gravity theories predict slightly differently. Einstein most ruled out other tests, but some survive. 44-minute source gravitational wave signal deviating general relativity prediction force rethink. Emission mechanism itself, possibly new physics if involving processes exceeding current models. New acceleration mechanisms operating. Key details. Long-period transients connect broader questions: compact object field creation and maintenance. How white dwarfs acquire billion Gauss fields. How neutron star fields evolve hundreds thousands years. Questions time magnetohydrodynamics. Stellar interiors. Each answer requires understanding under extreme conditions. For example, neutron star crusts, crystalline lattice, neutrons and protons densities exceeding atomic nuclei. Lab physics cannot recreate rely theoretical extrapolations. Observations objects, like 44-minute source test extrapolations. Binary evolution and tidal physics well established, but not fully understood. Close binary pairs lose energy tides and gravitational waves eventually merging. Timescale depends mass, size, interior structure. Observed predicted evolution rate discrepancies indicates missing model factors. Energy budget implications too. If standard power source is insufficient, missing something fundamental, perhaps magnetic fields store energy ways current theory not explain. Perhaps extreme conditions operate differently, model predictions. Perhaps beyond standard model particle physics relevant high field strengths. None impossible, well-tested physics. Standard model and general relativity has every challenge, but tests probe limited regimes. Strong fields, superdense matter, ultra-compact binaries beyond most lab and observational tests. New physics, if exists, may reveal. 44-minute source provides cosmological insights to compact objects, stellar evolution remnants. Properties depend birthing stars. Those stars formed gas-enriched prior generations. Chain traces back universe first stars. Understanding compact object populations tracks galactic chemical evolution and star formation history. How many magnetars exist? How many white dwarf binaries? Answers constrain galaxy evolution models. Inform predictions, distant universe, direct compact object observation impossible. Broadly, every anomalous astronomical object natural experiment cannot build white dwarfs or neutron stars. Labs cannot create atom warping magnetic fields. Nature performs experiments us. Job careful observation and accurate interpretation. 44-minute source, such experiment showing physics operating irrecapturable conditions, whether confirming current theories or revealing gaps, both outcomes advance knowledge. Why astronomers excited strange objects, not curiosities. Windows fundamental physics, opportunities test, understanding against reality. Universe, ultimate laboratory and fortunate telescopes, allowing observation experiments. Period regularity feels to perfect, to intentional, but not extraterrestrial intelligence signal. Every few years, astronomical discovery sparks extraterrestrial civilization speculation. Fast radio bursts did, Tabby star did, Oumuamua did. Now some ask if 44-minute source artificial. Answer no with near certainty. Several factors rule artificial origin first. Signal carries no information, simply periodic radio and X-ray emission. Nothing more. No modulation patterns, no embedded messages, no structure suggesting intentional communication. Lighthouse, not language. Second, natural astrophysical processes easily explain periodicity, rotation, and orbital motion. Birth periodic signals universe-wide. Pulsar pulses, eclipsing binary stars. Sunlight reflecting tumbling asteroids. Falling periodicity common, not rare or mysterious. Third, physics operating source incompatible technology. 100 million Gauss fields shred ordinary materials. No known or imagined engineering operate conditions. Radiation environment alone melt or vaporize machinery. Fourth, emission extremely energetic, but communication inefficient. If extraterrestrial civilization sending signal, use far less energy and structured transmission. Randomly blasting 10^32 erg/second space waste unimaginable. Fifth location, unremarkable galactic plane, amid countless stars, not near special position or range specific targets. If intentional signal, expect directed somewhere or strategically placed, simply where some compact object happens. SCTI community dedicated extraterrestrial intelligence search, unconcerned 44-minute source not matching artificial signal profile. Field researchers no distinguish natural astrophysical phenomena, potential technosignatures. This firmly natural category. Why periodicity feels intentional, perhaps humans pattern seekers. Evolved notice natural patterns predict fruit ripening or prey migration. Regular patterns catch attention, sometimes imagining agency absent. 44-minute cycle precise, yes, but countless other natural cycles to Earth rotation precise. Cesium transition atomic clocks even more. Precision alone not design often arises simple physics operating consistently time. That said, astronomers not dismiss extraterrestrial intelligence search SETI legitimate science posing important questions. If intelligent life exists elsewhere, possibly producing detectable signals, we should look. But recognize natural phenomena seeing them. 44-minute source teaches stellar physics, magnetic fields, compact objects, not extraterrestrial civilizations. Conflating misses true scientific value. First detected 1967 intriguing pulsar, similar speculation sparked pulse regularity seemingly perfect. Researchers briefly considered artificial origin, even nicknamed first LGM, one little green men. Months later, more pulsars found natural explanations emerged. Regularity, understood rotation not signaling. Long period transients following same path initially mysterious, eventually understood natural compact object physics consequence. Mystery not artificial, or not, but exactly natural process birthing them. Difference matters, because public fascination aliens sometimes overshadows real science. Media reports focusing mysterious signals sans context create misleading impressions. 44-minute source mystery meaning scientists yet fully explain, but not inexplicable or supernatural. Nature stranger imagined, but not stranger understandable. Enough observations, enough data, enough careful thinking natural phenomena yield explanations. Source 2. Universe full wonders, needing embellishment. Dead star broadcasting clock precision, 15,000 light years away, remarkable enough sans aliens. True story astrophysics story more interesting fiction. So while extraterrestrial intelligence speculation headlines, scientists focus real physics measuring field strengths. modeling emission mechanisms, calculating orbital parameters, building understanding observation and theory that progress happens, and when mystery finally resolved, when understand object what and how works, not diminish wonder enhance it, knowing nature births such phenomena, how far satisfying leaving unexplained, answers coming but unexpected direction, perhaps breakthrough technology new, telescope unprecedented sensitivity, detect dozens other long-period transients, revealing invisible patterns current small sample. Statistical analysis show all examples sharing traits suggesting specific model. Perhaps observation optical counterpart, finally identified 44-minute source. Spectrum reveal chemical signatures definitively linking white dwarf binary, or excluding possibility entirely. Companion star properties constrain system mass and age. Perhaps theory someone developed new model naturally explaining long period transients, sans special assumptions, fresh view magnetic fields, evolution, or binary interactions illuminate current theories missed. Solution simple, once someone thinks it, perhaps from wholly different field LISA gravitational wave detection, confirm 44-minute binaries orbital motions. Neutrino detectors catch rare reconnection event emissions. Gamma ray observations reveal even higher energy sporadic processes. Perhaps source itself changes sudden brightening or complete shutdown. Transition provide crucial nature information. If cycle detectably changes, change reveal physical processes altering mechanical clock. Variability possibilities constrain models as much stable behavior. Perhaps another long period transient does spectacular flaring dramatically releasing gigajoules minutes. Suddenly starting pulse after years silence, exploding or merging catastrophically revealing true nature. Such events provide extreme physics snapshots. Perhaps answer, already hands buried improperly analyzed data. Archives hold decades observations hundreds telescopes. Reprocessing old data, new algorithms reveal 44-minute source, seen years pre-official discovery. Historical data extend timeline, show long-term evolution. Perhaps breakthrough collaboration teams combining expertise radio astronomy, X-ray astrophysics, stellar evolution, plasma physics piece full picture together. No single discipline holds all answers solution, integrating details multiple fields. Perhaps requires patience, some astrophysical mysteries decades resolve. Neutron stars predicted 1930s, unobserved until 60s. Black holes theoretical curiosities, until X-ray binaries revealed presence. Long-period transients require similar patience, pre-revealing secrets. Science process not always linear progress accumulation observations, hypothesis testing, theory refining. Sometimes breakthrough sudden, sometimes understanding gradual years, either way. Persistence rewarded, 44-minute source not mysterious forever, to many researchers working it, to many telescopes observing it. Too much data accumulating. Eventually someone pieces correctly. When happens, textbooks updated, new questions emerge, discovery opens more research avenues and closes book. Way science works answering one question reveals 10 more. Each solved mystery illuminates farther mysteries. Currently source continues pulsing every 44 minutes, 2 minutes on, 42 minutes off oblivious human curiosity. In different theoretical debates, broadcasts emptiness, we listen, we measure, we wonder and somewhere data. Unmade observations, unrealized insights answer waits, 44-minute source tells secrets we just need right questions. Universe patient not rushing reveal workings, but not hiding them either. Everything discoverable if look carefully enough, and think deeply enough. This mystery lighthouse piercing darkness 15,000 light years teaching us we just need learn language. Next chapter story writing now observatories worldwide, telescopes skyward, data flowing, algorithms processing, scientists analyzing, theories evolving, understanding growing and someday soon someone finally say, I know what it is. That day cannot come soon enough.